Good evening. On behalf of Engineers Australia, I am delighted to welcome you all to our Thought Leader series, Designing with Double Wall Precast Panels. My name is Jamie Burridge and I am the General Manager for the Sydney Division at Engineers Australia. I am delighted to welcome you all here today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to their elders past, present and emerging. Right now, where I'm stood, that is the Gadigal people of the Eora Nation. Now, before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Austral Precast. Austral Precast is the leading provider of high quality and innovative customisable precast concrete product solutions. It services a range of markets including multi-residential, commercial, industrial, community and civil sectors. I'd now like to welcome Michael Monroe from Brickworks Building Products and Austral Precast.
Good evening, and on behalf of Austral Precast and Brickworks, welcome to tonight's event. My name is Michael Monroe, and I'm the Communications Manager for Brickworks Concrete and Facade brands, which includes tonight's sponsor, Austral Precast. Austral Precast are Australia's leading provider of precast concrete solutions. We offer a range of walling, flooring, columns and beams, as well as customised precast concrete solutions. But what makes us really unique are products like the topic of tonight's presentation, double wall. We also offer an innovative solution called panel brick, which combines the natural beauty and longevity of clay bricks with the speed and efficiency of precast panels. We're part of Brickworks, which includes a range of leading building product brands offering bricks, roof tiles, facade systems, masonry blocks, retaining walls, and pavers and stone. We make quality products that create beautiful environments. I'd now like to share with you a short video about our business.
Strong, secure, everlasting, innovative, resilient, stylish. Throughout the past 110 years, the face of building materials has continued to evolve. We're here for a lifetime of living. This is Brickworks. More than brick, and more than just building products, we are a foundation for today's lifestyle and a leader for today's style. We manufacture a wide range of building products like no other, local and international innovation, sourced from around the world to exceed customer expectations. Bricks, roof tiles, pavers, masonry blocks and retaining walls, precast concrete, concrete sleepers, stone. Distinctive and luxurious products, beautiful products that stand the test of time. Our pursuits have no borders. We continue to expand internationally with an increasing portfolio of brands in North America, including Glengarry, Sioux City Brick, Lawrenceville and Cushwa. More than just building, we're building with confidence. Sustainable manufacturing and products that are shaping our future. We are committed to conducting business that best serves the interest of the community and the building industry, so that we create strong and enduring relationships. Brick continues to inspire some of the most incredible architecture and engineering around the world. Designed and developed through product partnerships with leading architects. Custom and bespoke products for endless design creativity. We are helping to shape the architectural landscape. Sustainable, distinctive, robust, customizable, building the impossible and turning designs into reality. Everlasting expressions of colour, texture and form. Not just a building process, but an intimate and personal statement of style, colour and lifestyle commitment. constructing places of creativity, hubs of inspiration, places of possibilities. Our design studios continue to evolve. Sydney, Melbourne, Brisbane, Adelaide, Hobart, Perth, and coming soon, Philadelphia and New York. Providing a one-stop shop for products, design advice, industry-leading events, and thought leadership discussions. Attracting like-minded individuals, creating partnerships, inspiring style, informing thoughts, and evolving our industry. Over 110 years of experience, a suite of market-leading brands, building inspiration and innovation with an unmatched standing of style. This is Brickworks.
I would now like to hand back to Jamie to introduce tonight's speakers.
Thank you, Michael. I'd now like to welcome our first speaker, Angus Mcfarland. Angus is structural engineering leader in Laing O'Rourke and specialises in the design of high-rise and ultra-tall buildings. In addition to being a Fellow of Engineers Australia, he is also a Fellow of both the Institution of Structural Engineers and the Institution of Civil Engineers. Angus's projects include the Burj Khalifa, Emirates Towers, Burj Al Arab, Dubai Festival City, and Dubai Marina in Dubai, UAE. ADNOC HQ Office Tower in Abu Dhabi. Please welcome Angus Mcfarland.
Good evening, ladies and gentlemen. My name's Angus Mcfarland, and I'm Structural Engineering Leader with Laing O'Rourke. I'm here tonight to talk about the design of double-wall precast panels. I'll briefly talk about the contents of my presentation. I'll start off with an introduction, which outlines part of my career. Then I'll talk about DFMA technical specifications. Then actually answer the question, what is double wall? I'll then go on to speak about some construction details, then transportation and delivery, temporary works, and finally, I'll talk about some case studies. A brief introduction about my career. I came to Sydney about 10 years ago to work with Laing O'Rourke, and one of the first buildings I worked on is Mount Street, which is our head office. Before that, I was technical manager with B6 in Hanwha and Seoul for about a year. But my main part of my career prior to working for Laing O'Rourke was with Hyder Consulting, and I spent about 20 years in the Middle East. And also in the Middle East, I spent some time with W.S. Atkins. Here are the three main projects that I liked about my time in the Middle East. The first one is the Burj Al Arab when I was with Atkins. And little did I know it at the time, that was my second once-in-a-lifetime project. But I moved on to a few more once-in-a-lifetime projects. The one on the right-hand side, which is the Burj Khalifa, which I think is still the tallest building in the world, but it won't be for long. And the middle one is my favourite project in Dubai. That's the Emirates Towers. These are two towers. The left-hand side one is a hotel tower that's built by B6, and the right-hand side is an office tower which was built by Multiplex. This was my favourite job because the team got on very well together. The project was completed 3 months early and within budget, which is quite unusual in the construction industry. I'll now go on to my first experience of twin wall. And I use the term twin wall and double wall interchangeably. Twin wall is Laing O'Rourke's version of double wall. Austral call their version double wall. The first time I came across it was when I had to peer review Laing O'Rourke's design calculations. Then I did the testing of a trial tank, which you can see on the right-hand side. That was built in the car park of Laing O'Rourke's facility at Steatley in the middle of England. And this was a proof of concept for use in Beckton treatment works in London, the UK. I'll go on to Beckton later on during the case studies. DMFA technical specifications. Now, this is a project that we've been doing with Standards Australia. The project went to sleep about 2 years ago when the representative, Alison Scotland, left Standards Australia, but it's revamped recently, about 3 months ago, with a new representative taking it over. The first one's intended to be progressive collapse, loading, and precast wall panels. Now here we have progressive collapse. This is a project from a PhD project number 3, and this was a project that some students did in Monash University when I was a member of the Modular Construction Code Board. Not only a member, I was actually chairman. Now what you can see there was just a slight difference in the size of columns. If we go from 200 by 200 columns to 300 by 200 columns, we get no progressive collapse. Second thing is transportation loading. AS 3850.2 gives some guidance, especially on road transport and erection loading, but you need further guidance, especially shipping loading, since a lot of our structural elements come from overseas nowadays. You also need rail transport and fatigue loading, etc. And here's a large roof structure that was built in Hong Kong by engineers Robert Bird. Now finally, this is actually the first technical specification we're doing, and it may very well be a standard. And as part of this work, I prepared a facsimile of the code, British EN 14992, which is precast wall elements. And this will include design rules for double wall. It's currently with CEN for approval. That's the Committee European Normal, I think, the people who run the European standards. Once that's approved by them, we'll publish the facsimile and then agree it with stakeholders here in Australia. Now, one of the reasons why we need this standard is some consulting engineers accept double wall can be fully composite, whereas other consultants don't. So as part of the stakeholders, we would like to include those engineers who are reticent about it. What is double wall? Well, it's a composite wall. It comprises 2 precast concrete shells, sometimes called them biscuits, joined together by a lattice girder system, and on site we fill the space between the shells with in situ concrete. The stage 1 is the first shell is cast, and the mesh and trusses are cast into the biscuit or shell. The second stage is the first biscuit is lowered onto the wet concrete in the second biscuit, then it's vibrated to form the double wall complete shell, the complete unit. Typical details of the double wall showing the shell reinforcement, and the lattice girders. Now, it's best, if you can, to put all the reinforcement you need into the shell, apart from the stitching together reinforcement. But occasionally, if you've got very heavy steel, you might need to put some reinforcement in the gap as well. Now, here is a short video of our facility in Steatley in the UK. This video doesn't have any sound, but it does have some captions on it, so I'll only interject if it needs some explanation. The factory is very highly automated. There are very few people required in it. We do require people, we can't get away without people, but we use a lot of robots in the factory. Now, the factory is linked to the computers, so we have our 3D models, which then get transposed to the computer, which then produces digital models for the robots to work from. I think this numerical control the 3D models get changed to numerical control instructions for the robots to work. Now the curing chambers are typically, you put the fresh concrete units into there and for about 18 hours when they're fully cured. Now we have the twin wall product. That's the first biscuit, or the first shell. Then you've got the wet shell. Then you bring the biscuits together. Now this is the biscuits coming together here. I think you can hardly see that. No, that's the biscuits coming together now. And we should have got more detail in there. Unfortunately, we don't actually get the detail of the biscuit going into the wet biscuit. So that's how double wall is made. Now, designing and testing, I was involved in this, as I've said, with the trial tank for Beckton. But in addition to checking the design, there are other tests, various characteristics of the double wall, such as roughness, strength of the core and shell, embedment depth, and diameter lattice trusses. These were all varied to find out which was best. Now here are the results from some tests. On the left-hand side, you can see 50-50-50, which is 50 shell, 50 in situ, 50 shell. Another one which is 50-10-50, that's 50 shell, 10 MPa in situ and 50 MPa. And then the third one is 10-10-10. You wouldn't do that, but you wouldn't do that in practical sense, but that was done to give a wide variety of parameters so we could check out if Eurocode design is safe, which it is. We also tested in situ core shell interface with very smooth profile, a smooth profile, and a rough profile. And the normal profile would be the rough one on the right-hand side, which you can see that the Eurocode value is about half the actual value we get when measured. Now, it's safe to use Eurocode, and here's the Australian concrete code, AS3600, and this table is lifted straight out of Eurocode. They only change the name of the parameters, mu and KC0. Now, from the tests that described in the previous slides, it's safe to use a coefficient of friction mu of 0.7 and a coefficient of active pressure 0.4. However, you probably find in Matthew's slide that Austral prefer to use 0.6 and 0.2. But if you cast your mind back to the testing slides I showed about 3 slides ago, we could probably go double the 0.7 and 0.4. So using 0.6 and 0.2 is very safe. Now, we'll now talk about construction details. This is, construction details are how do you stitch the precast panels together. Now here's a vertical joint. So you drop in that cage shown in blue, and on the right-hand side you can see you drop it in for a lap length on either side of the horizontal joint. Corner joints are very similar to the corner joints you'd have in situ. The one on the left-hand side is just like an in situ corner joint detail. Again, that's a prefabricated cage and you drop it in. Less common is just using a single bar. You can use it occasionally, but most designs would require the detail on the left-hand side. And I show a steel plate in blue, which is sometimes attached to the wall, especially if they're high wall lifts, double wall lifts, or if you want to have a very high pour rate of the in situ concrete. Again, a variation on the joints and walls. This is the T-joint. Again, it's just dropped in from the top, and then we concrete the thing together. Now, in situ slab connections It's best to stick to floor height if you can, and avoid double wall height unless there are no intermediate slabs at mid-height. Occasionally you'll go double height, as I say, if there are no intermediate slabs. Also, the continuity reinforcement is placed after the construction deck the working deck is placed. This is assuming you're using an in situ slab. And it's always good to extend the outer edge of the double wall to form a permanent shutter, so it's used as edge formwork. And it allows the full effective width of the wall to be used in the design calculations. When it's a lattice plank, a hollow core plank, or bond deck, or etc., slightly different details, you oversail the top of the wall as shown there. This allows you tolerances in your slab construction. The joint between the top of the wall and the underside of the slab system can be grouted if it's precast, especially if you need to use the full wall strength in the design calcs. However, a personal choice of mine is a neoprene gasket attached to it, and you just design for a reduced effective width of the wall. And now we get on to transportation and delivery. Panel height is normally the governing transportation limit. Typically 3.5 meters high is the maximum without a police escort. Panels are usually 330 kilograms a square meter, so you can get up to 3 panels on a trailer. That would be approximately 20 tons or 60 square meters of wall. Now I show the safe access ladders here. This greatly speeds up the people working on site, fixing the crane cables to the precast. And there we see the panels being lifted from the trailer quite quickly. Now we go on to temporary works. Now the temporary works are limited. It's usually just back propping, but it's best to sequence the props after the permanent slabs are cast. You can do temporary concrete blocks or trenches or whatever, but it's usually far faster to prop from the permanent slab, and you use cast-in sockets in the double wall for fixing the props. And for safety, you need to protect the barriers from any possible impact from vehicles if there's vehicles in vicinity of their props. Corners may require some steel brackets for high concrete pour rates. I showed that earlier on the detail. Or you may need to fix plywood on site for corners, as shown there, or you can cast mesh into the double wall during the manufacturing process. And something else you can do is a specifically designed end shutter for double wall. That can be installed in the factory, and it eliminates the need for formwork on site. I'll now go on to the case studies. Now, the first case study is a university library building in Durham in the UK, a laying O'Rourke job in 2010. The reference design was in situ, and we won the tender by changing it to completely precast. It's a fully precast solution, precast piles with 119 twin wall panels, precast slabs and precast columns, etc. Now here are some details from the library building. This shows the core wall, and I've shown that to highlight you don't need to be rectangular core walls. You can have various shapes you want as long as they're made out of straights. And on the right-hand side, you can see the different mixture of panels, one in blue and one in grey. Now there's the actual photograph of the core walls being constructed. And you can see it's very similar to that shown on the model. Now there's the thing I mentioned earlier. You very rarely go to double height, but these 4 walls here, which were a feature, they are double height twin wall panels, and you can see the double row of propping. There's mesh inserts to avoid us using stop-end shutters, and a small scissor lift was used to pour the concrete immediately after installation. Now, I touched on this one during my experience slides at the beginning of this presentation. This is Beckton Treatment Works, and at the time it's the largest treatment plant in Europe, and I still think it is. The total cost was £350 million, which is around about $700 million Australian. There is the array of double wall aeration tanks there. And now I compare them to the testing panels that I did earlier on in 2010. What I didn't mention in that one when we're doing the test on the left-hand side, the wall you see there is horizontally spanning twin wall units or double wall units. On the other side, we're vertically spanning to see which one performed best. And on Beckton, they used the horizontally spanning walls, as I've described just now. The original design was in situ concrete, 700 thick at the bottom and 525 at the top. The twin wall used buttress walls, horizontally spanning onto, I think they were 1.2 metre wide buttresses. The reinforcement saved was 50%. The saving in concrete was 10%. There was a large programme saving as well, but I forget what the programme saving was. The unfortunate thing is I didn't get to design this the aeration tank final design. Because I was working at Dubai at the time, I had to pass the design over to Hyder in UK, who went back to rediscovering the wheel, ignoring all my work and whatever. So Arup actually got the final design. I should perhaps have stood up a bit stronger to the Hyder board in London and say, look, I'll run it from Dubai, using a small team in London and a small team in Dubai. Anyway, we didn't get it, but it's good that a leading consultant got it, Arup, and they totally embraced the double wall concept or the twin wall concept. Now, closer to home in Sydney, this is the ETP in Sydney. That's Engineering Technology Precinct at Sydney University. And we're using double wall there. Now, it was used in the basement. We also wanted to use it in the core walls of the building. It's 11-story building, the ETP building. But the engineering consultant, Cardinal, didn't want to use it in core walls. So I harked back to why we need the Standards Australia specifications or standards so we can use double wall as core walls. In the UK, that is our element of choice, is in core walls. And some of our projects here in Australia, where the engineers look on it favourably, will use double wall and core walls. The benefits of double wall is that it provides the flexibility of in situ concrete, but there's no shuttering on site and it's quick to erect. Now, we've looked at it for other jobs as well. Here is a mining project in WA in the Pilbara region. This is a large, it's a primary crusher for the rock aggregate. The rock gets crushed and made into aggregate. Well, it's not aggregate, it's actually iron ore. It gets crushed to eventually become iron ore. We looked at various options for this. The reference design is a large in situ crusher shell. We looked at double wall, shell wall, and solid precast. And the double wall solution was most cost effective. The costs were about 20% higher. That's because Austral didn't have a factory in WA that can produce double wall. Their precast factory in Perth doesn't produce double wall, it produces other precast units. So the reason for the 20% uplift was it had to be shipped from Sydney to Port Hedland, then taken by road to site. However, there's a 10-week saving in programme of the double wall, and the programme savings outweigh the higher cost of the double wall. I'm still not sure if that's been built yet, but I'll check up. I think it's still in abeyance. Now, summary, installation programme. So you'll plan for one unit to be placed every 30 minutes. On site, they can go faster than that, but it's better to allow 30 minutes just in case something goes wrong. I'd always recommend using self-compacting concrete with a slump flow of about 500 to 700 millimetres. Matthew can give you his recommendations on what he prefers to use, and I would recommend 10 millimetre aggregate. And keep the walls simple. It's possible to cast items in during the manufacturing process, but where possible I'd avoid this, because if it gets cast in the wrong place, it's difficult to fix. Simple means quick, less work in the design and coordination, and it's reliable results on site. Express joints. If the joints are to be visible, remember it's a precast product, so try and keep the joints simple, only express one of the joints, either the vertical joints or the horizontal joints. I would suggest you don't try and express two, because you can get slight misalignments in them, which looks very obvious if it's actually visible to people inside the building. Now, this is the last slide. I reiterate, the key benefits of double wall is it has the flexibility of in situ concrete, but the speed and simplicity of precast. Thank you very much, ladies and gentlemen.
Now that's all the time we have for today. Please join me once again in thanking Angus Mcfarland for their time and input. I'd like to thank Engineers Australia's industry partner, Austral Precast, for their support. Thanks again for joining us. We look forward to welcoming you to our next Thought Leaders event. Thank you.